percentage for the cut-off ABC?
C was 24.5, B was 31.9, and A was 41.7. Okay, so the idea of gravity. We looked at this the other day. We actually use this formula, G M1 on M2 on R squared, to help us determine the mass of the Earth. Okay? Now, given that we did that, we made a few assumptions, like the fact that we knew the value of the gravitational constant here. And if we're going to find out the force of gravity between any two objects, it doesn't matter what those objects are, whether they're oranges that far apart or whether they're planets thousands of kilometres apart, they are going to exert a gravitational force upon each other. So every massive object is going to exert a gravitational force on every other massive object, but clearly it's going to be the size of the object and the distance apart is going to determine whether there's going to be a negligible force or not. So, what is gravity? If you've got two objects here, M1 and M2, and you've got the distance d between them, then your force is equal to G times M1, M2 on d squared. Now, dealing with that, we have the gravitational constant, and in this case, the gravitational constant is 6.67 by 10 to the minus 11 Newton metres squared per kilogram squared. Now, just to give you a bit of an idea how small a force that's actually dealing with, if I have F equals G M1 M2 on R squared, supposing I have these, I don't know why, but apparently students who think it's nice to actually turn the stopwatch alarm on, apparently that is not a crime that is punishable by death. I'm very disappointed about that. So for instance, if we have, is that cracked up there? Notice again, if we have two 1 kilometre masses here, and they're 1 metre apart, so using this formula, they should actually have some sort of attractive force between them. So you sit them there and go, honk like that. How big a force is it between those two things? Well, let's have a look. The force is equal to G times mass 1 is 1 times 1 all over 1 squared. So in that case, force is equal to G. So the force will equal 6.67 times 10 to the minus 11 newtons. Wow. So there is a force of attraction between those two things there, but it's not terribly strong. It only really comes, well, not only really becomes significant, but it becomes really significant when you're dealing with something that is one of either one or two of these things, which is hugely massive. And then we get to see what's going on. Okay. On your information sheet, don't panic too much. It's written as this. This one's got d squared, and that's one that's in the textbook for distance. the only information you've got R squared, I wouldn't imagine that would cause any issue. Okay, so this gravitational constant, 6.67 by 10 to the minus 11 Newton metre squared per square kilogram, it's a very tiny amount. And you can see that if I had these things here, the fact that I've got these two masses 1 metre apart, then what we're going to have here, and you're going to be measuring a force down to 10 to the minus 11, you're going to need some really fancy equipment to be able to measure that sort of tiny forces. And the man for the job was this bloke here, Henry Cavendish. And it was first proposed in Newton proposed the idea with he came up with his universal law of gravitation, but he had no way of being able to determine what the gravitational constant was. He had an idea about it was, but he had no way of proving it, because the sophistication of the experimental equipment they had was in no way capable of getting down to these very fine levels. It wasn't until Cavendish came along and actually set up what was basically a flour mill, and it's been exploded out here. Obviously the wall was still there. He set up two huge lead balls on a big pendulum, okay, with two other lead balls, and by knowing the distance between them and knowing the mass of these balls, was able to actually do an experiment to determine G, and got that down to a level that was within 1% of accepted levels today. Now, I must admit, Henry Cavendish is a bit of a favourite of mine, and even by the standards of the day, he was a fairly odd character. Has any of you ever read Bill Bryson's A Short History of Nearly Everything? Right. We should. It's good. So, let me see. But for all that Michael's another William Herschel. Michael produced the equipment here, but never got to use it properly. For all that Michael accomplished, nothing was more ingenious or had greater impact than a machine he designed and built for measuring the mass of the Earth. Unfortunately, he died before he could conduct the experiments, and both the idea and the necessary equipment were passed on to the brilliant but magnificently retiring London scientist named Henry Cavendish. Cavendish is a book in himself. Born into a life of sumptuous privilege, his grandfathers were dukes, respectively, of Devonshire and Kent. He was the most gifted English scientist of his age, but also the strangest. He suffered, in the words of one of his few biographers, from shyness to a degree bordering on disease. Any human contact was for him a source of the deepest discomfort. Once he opened the door to find an Austrian admirer, freshly arrived from Vienna, on the front steps. Excitedly, the Austrian began to babble out praise. For a few moments, Cavendish received the compliments as if they were blows from a blunt object, and then, unable to take any more, fled down the path and out the gate, leaving the front door wide open. It was some hours before he could be coaxed back to the property. Even his housekeeper communicated with him by letter, so a fairly shy, odd sort of bloke. Although he did sometimes venture out into society, he was particularly devoted to the weekly scientific soirees of the great naturalist Sir Joseph Banks. It was always made clear to the other guests that Cavendish was on no account to be approached or even looked at. Those who sought his views were advised to wander into his vicinity as if by accident, and to talk as if it were into a vacancy. If their remarks were scientifically worthy, they might receive a mumbled reply, but more often than not they would hear a peeved squeak. His voice appears to have been high-pitched, and turn to find an actual vacancy and the sight of Cavendish fleeing for a more peaceful corner. So a pretty odd sort of bloke. So his wealth and solitary inclinations allowed him to turn his house in Clapham into a large laboratory where he could range undisturbed through every corner of the physical sciences. Electricity, heat, gravity, gases, anything to do with the composition of matter. The second half of the 18th century was a time when people of a scientific bent
grew immensely interested in the physical properties of fundamental things, gases and electricity in particular, and began seeing what they could do with them, often with more enthusiasm than sense. In America, Benjamin Franklin famously risked his life by flying a kite in an electrical storm. In France, a chemist named Pilatre de Rosière tested the flammability of hydrogen by gulping a mouthful and blowing it across an open flame, proving at a stroke that hydrogen is indeed explosively combustible and that eyebrows are not necessarily a permanent feature of one's face. Cavendish, for his part, conducted experiments in which he subjected himself to graduated jolts of electrical current, diligently noting the increasing levels of agony until he could keep hold of his quill and sometimes his consciousness no longer. So, you know, fairly odd sort of bloke. But our interest here is in Cavendish's last known experiment, where in the late summer of 1797, at the age of 67, he turned his attention to the crates of equipment that had been left to him, evidently out of simple scientific respect, by John Michell. When assembled, Michel's apparatus looked like nothing so much as an 18th century version of a Nautilus weight training machine. It incorporated weights, counterweights, pendulums, shafts and torsion wires. At the heart of the machine were two 350-pound lead balls which were suspended beside two smaller spheres. The idea was to measure the gravitational deflection of the smaller spheres by the larger ones, which would allow the first measurement of the elusive force known as the gravitational constant, and from which the weight, strictly speaking the mass, of the Earth could be deduced. And I'd just like to say it's got an asterisk down here. To a physicist, mass and weight are two quite different things. Your mass stays the same wherever you go, and your weight varies depending on how far you are from the centre of some other massive objects like a planet. Travel on the moon and you'll be much lighter but no less massive. On Earth, for all practical purposes, mass and weight are the same, and so the terms can be treated as synonymous, at least outside the classroom. Well, that's just tosh. I don't believe that's the case at all. You should be very, very firmly of the view that mass and weight are not the same thing, and the fact that that's been put in our book is a blow against it. Because gravity holds planets in orbit and makes falling objects land with a bang, we tend to think of it as a powerful force, but it isn't really. It's only powerful in the kind of collective sense, when one massive object, like the Sun, holds onto another massive object, like the Earth. At an elemental level, gravity is extraordinarily unrobust. For each time you pick up a book from a table or a coin from a floor, you are effortlessly overcoming the gravitational exertion of an entire planet. What Cavendish was trying to do was to measure gravity at this extremely featherweight level. Delicacy was the key word. Not a whisper of disturbance could be allowed into a room containing the apparatus, so Cavendish took up a position in an adjoining room and made his observations with a telescope aimed through a peephole. The work was incredibly exacting, involving 17 delicate interconnected measurements, which together took nearly a year to complete. When at last he had finished his calculations, Cavendish announced that the Earth weighed a little over, well, it's got however many pounds that is, but it's got 6 billion trillion metric tonnes, or 5.98 times 10 to the 24 kilograms. Today, scientists have at their disposal machines so precise that they can detect the weight of a single bacterium, and so sensitive that readings can be disturbed by anyone yawning 75 feet away. But they have not significantly improved on Cavendish's measurements of 1797. The current best estimate for the Earth's weight is, mass should be, is 5.9725 billion trillion tonnes, or 5.9725 by 10 to the 24 kilograms. A difference of only 1% from Cavendish's finding. Interestingly, all of this merely confirmed estimates made by Newton 110 years before Cavendish without any experimental evidence at all. So there you go. So, if you've got a bit of loose end, there's all sorts of fun things, fun facts in there. Now the beauty about that, so these two large, basically on a torsion bar, there and one there. And so the force of attraction due to gravity between those causes that to twist. And by measuring the force in that causing that to twist and knowing the mass of these, then he was able to come up with a estimate for the gravitational constant. He was in a science oddball, right? So, and if you're feeling a loose end, you can actually get them. Torsion balance is just like Cavndish. They look a little bit like that. These two things here. So the two large balls and the two smaller ones, you move those over there. It's got suspended down on a very fine wire. In fact, we even have one here. So, if I cast your eyes this direction. So, over here, we have a couple of lead balls, and you can see there's little lead balls in there. By moving those lead balls over to one side, then there's going to be a gravitational attraction between the big lead balls and the small ones, and that will twist the whole, torsion bar, so it's actually going towards that side. If I pull it back over this way, then what happens is, very clever of them. Okay. Actually set that up. So that now it pulls it back over this way. So what happens is, if I pull that over there like that, and I shine it, it's got a little mirror attached to the wire, or a little bit of fishing line that runs down the centre of that. If you bounce a laser off that, so, laser bounces off there, bounces off that wire, and the fact that it's actually running across the length of the classroom now, and bounces onto the whiteboard there. If I switch that round the other way, I strongly suspect that the ball is going to get in the way of the laser. Oh, there it is. So, it's actually dragged it over by millimetres, which is what you would expect. It's not going to be a huge, despite the fact that the distance between those, and there's two of them, the two large lead balls are quite massive, the two smaller lead balls aren't quite as massive, but the distance between them is quite short, so we've cut that right down, so that what we've actually done is, by turning that round, it's going to twist the mirror one way, and pulling back around, it's going to twist the mirror the other. It's actually quite still. If you hear a truck go past, it'll actually vibrate that enough, so it'll actually go back to where it was. So even though the truck's 50 metres away, then that's how sensitive it is that we're looking at there. It's not really enough to do quantitative method. We actually do the numbers, we actually work out the numbers for it. It's the number one, quantitative. Yeah. It's not enough to do quantitative measurements, but it's enough to give you the idea. So let's have a look at an example. This is going to be reasonably straightforward. The force of attraction between the Earth, which is the mass of 5.98 by 10 to the 24 kilograms, and the Moon, which is the mass of 7.35 by 10 to the 22 kilograms, given that the Earth-Moon distance is 3.8 by 10 to the 8 metres. Alright. If
F equals G M1 M2 on R squared. Plug in the numbers. And we have 6.67 by 10 to the minus 11 times the mass of the Earth, mass of the Moon and the mass of the Earth divided by the square of the distance between the centres of mass of the two objects. Not from the surface to the surface, but from the centres. And what we find out is that there is a force of attraction 2.07 by 10 to the 20 newtons. And that is an unbalanced force. If that's an unbalanced force, then why isn't the Moon smacking into the Earth and making a mess?
Because it's falling forward.
It's falling.
Well, it's moving forward as fast as it's falling
That's
towards
right.
the Earth.
Exactly. It's actually got it. So this is providing the unbalanced force that provides the centripetal acceleration so that it can continue to orbit the Earth. Okay. So, have a crack at questions 19 and 20 on page 148.